Alright, so today's actual new topic is delightfully simple. We're going to crush this. We're going to call this types of reactions. And so this is going to feel like a little bit of sidestep. We've been doing a whole bunch with polyatomics. We will come back to polyatomics, no worries. And we're actually going to use them inside of the types of reactions. So since you know polyatomics already, have your eyes out for the polyatomics as we go through these types. Some types prefer to be associated with polyatomics more than other types. So like, what types of things are doing each type of reaction? Okay, getting ahead of myself. There are 3 types of reactions. That's not true. There are 5 types of reactions. Let's give you some little spots here. I've got a full PowerPoint on this also. I will link that for you as well. I should make a note to link that link to PowerPoint. That's also helpful and great, but I'm just going to walk you through it like this for here. Alright. 5 types. 2 are kind of reverses of each other. Like 2 sets are very related to each other, and then the 5th is an oddball on its own. Here we go. Sometimes things... Okay, I'm going to give you the names. These first 2 are opposites of each other. So you take a synthesis backwards, you get a decomposition. You take a decomposition backwards, you get a synthesis. They're linked in that way. So synthesis is kind of like your synthesis essay in English class. It's taking all the things you know, all the parts of all the things that you know, and it's combining them all together. So you'll sometimes see synthesis reactions called combination reactions. Those are both valid names. For our purposes, let's just call them, I'll give you both. They're also called combination. And they do exactly what you predict with that kind of a name. So you're going to take 2 or more, but some amount of like smaller compounds, multiple smaller compounds, combine to form a larger compound. We can even write that. Multiple smaller compounds combine to form a larger. That's synthesis. This is going to drive all of us nuts that I don't have enough space, so we're just going to make some more space. The second type is decomposition. Decomposition is the opposite of synthesis. Synthesis is 2 smaller things combining to form a bigger thing. Decomposition is 1 larger thing decomposing, breaking down into 2 smaller things. Don't overthink it. That's it. It's a larger compound breaks apart to form 2 or more smaller things. Okay. So far, so good. It may not surprise you, decomposition reactions frequently take in heat. Things like to be stuck together. If you're trying to break a compound, you usually light it on fire, right? Like, give it some massive form of energy. These take in heat. So when you're identifying some of these here, imagine yourself in the lab over a Bunsen burner just burning stuff. That is probably a decomposition reaction. We will not be doing that today, unfortunately. Sadly, they're kind of fun. You like make new stuff. Sometimes you make gas. It's a thing that happens. There's a lab where I make you burn baking soda. I don't know if we can do that from home. Let's take in heat. And heat is really just energy. Yeah, cool. Alright, those are your first two. Synthesis, smaller things come together. Decomposition, bigger things breaking apart. These next two are like, they're not linked, but they're related to each other. They're kind of, they go together, if you will. Here are their names. Some are single replacement reactions, and some are double replacement reactions. We sometimes act these out, as if we were in theater class. So, you can think of this as being at the school dance. That's fine. One couple starts together and another person is not involved. And as a result of the reaction, something happens. All of a sudden, you've got a different set of pairs going on. You can identify a single replacement reaction because one element starts single and a different element ends up single. So these are reactions where one element starts kind of by itself. This is usually something actually breaking down this thing. You'll see this a lot with acids and metals. Acid eats metal, great. And then afterwards, you've got a part of that acid attached to the metal and a flammable gas. That's a frequent way that you see these single replacement reactions. So one element starts alone by itself in its pure form. And a different element ends up in its pure form. Pure just means by itself. The chemists are into being by yourself or something. I don't know. So pure just means it's not stuck to anything else. Okay. So in a single replacement reaction, a single element gets replaced. You can think of it that way too. B starts with A, B ends up with C. That is a single thing getting the replacement done to it. In a double replacement reaction, you start with 4 types of things, and everybody starts paired. Everybody ends up paired, but a reaction occurs, a switch takes place. Let me give you this hint. These often happen with ions. So that original question of how are we going to merge this with what we just learned over the past few days, from ions that the first thing's always positive, second thing's always negative. So when these things go to react, that compound's positive ion is going to go stick to that compound's negative ion, and this compound's positive thing will stick to that compound's negative thing. This is the kind of thing that folks sometimes put on note cards just to remind yourself of. But you can also kind of see it. The first thing's positive sticks to the second thing's negative. Second thing's positive sticks to the first thing's negative. In a double replacement, all things, like all pieces, everything starts paired and ends up paired, but all of the pairs switch. Starts paired. Or in a compound, or I'm saying paired, but what I mean is like not alone. These are not pure things here. Everything starts in a compound and reacts to form new compounds. And it's a double replacement because two things like switch spots. In a single replacement, a single thing switches partners. In a double replacement, two things switch partners. So B has switch partners and D has switch partners. Or you can think of it as A has switch partners and C has switch partners. So it's a double replacement because it's kind of like a do-si-do. Everybody starts with somebody and then ends up with somebody else. Double replacement. Your fifth and final type is, I'm going to do this on a new page just to get a little bit more space. Your fifth type is the oddball. There's nobody that kind of goes with this one. These reactions go one way. They don't go backwards. They take a whole lot of energy to go backwards. These are combustion reactions. This is where stuff burns, blows up, explodes. Usually I write this, I'm like, what does combustion make you think of? All of those things are correct. This makes you think of fire. You know, we get stuff that we can light on fire, but to take it backwards from a combustion reaction, that takes some doing. Combustion reactions happen all the time. They are going on inside of you. Turns out you are taking in something and releasing something else in a whole bunch of forms throughout your body, things that you need to consume, and you can't respond to me because this is all video. You breathe in this, you breathe out that. You also take in, for breakfast, lunch, dinner, snacks, and anything else you eat, you take in, we're just going to go real general on that one, fuel. Fuel can be food. This is the type of fuel that you burn. You burn your food. When you think about burning calories, that's actually accurate. That is a combustion reaction. Your car takes in gasoline. You can burn wood in a campfire, anything like that. Anything you can burn, that's a fuel. Your candle's a fuel. Paper can be a fuel if you light that on fire. Kind of anything that will light on fire, that's a fuel. Fun fact, these are all super related to each other. They're almost all either, you're going to see a pattern here also. You are made of carbon. Your food is made of carbon. These are carbohydrates. Find some little words in there. Those are some carbon and some hydrogen. Or what you put in your car is a it's the same thing. We call them different words because, we want to be special or something. Carbohydrates, hydrocarbons, same deal. Fuels are usually carbon and hydrogen. That mixes well with oxygen, forms carbon dioxide, and usually I make you figure this out on your own. If you're taking in some carbon and some hydrogen, mix it with oxygen, that's where your carbon went. Your oxygen is also going to go stick to your hydrogen. Things you might be able to think of that have hydrogen and oxygen. Fire forms water. scratch your head on that one for a little bit. Yeah, it's a thing that happens. Turns out, combustion reactions take in fuel, oxygen, form carbon dioxide and water. And there you got it. These are also the most difficult to balance. So last quarter, when you were like, oh my gosh, this reaction is so difficult, how do I ever balance it? It's because you were attempting to balance and you did, you all got there. But yes, these are the most disgusting to balance, usually because the fuels are so complex. Yeah, that's a wrap. Those are your 5 types of reactions. I'll give you some examples. I'm going to go faster on their examples, I promise. See you soon.